Thank you, Charlie. Hello, everyone. Thanks for coming. Today, I'm going to talk about Hello 2 overview and thanks for coming. So I assume most of the audience comes from the ZCash background and probably learned about Hello 2 and want to explore it. And today I'll give a very high-level overview to lower your barrier of entry. And for this talk, I didn't do a lot of fact checks that to the degree that I'm comfortable. It's mostly from my brain dump, and if I miss something or didn't mention your contribution or some people's contribution, the errors are mine, and please let me know. I'm very sorry for that. So some basic info about me. You can call me CC. I'm working on a zkevm project with Astria, Ash, Barry, Carlos, David, Edu, Marius, Miha, Nick, Han, Honor, and Inton, and many others. People from ScrollTech and Loopring, and many external contributors. And about zkevm, the goal is to build a succinct validity proof for the Ethereum blocks. And it has two main usage. One, you can scale L1 full nodes with the proof, so the full node can verify more computations than it can now. So that means more transactions and more gas for computation. And the second usage is that you can use this validity proof to build the L2 ZK rollup that is Ethereum compatible. And to do that, we need a tool to build such a validity proof circuit. So we use Hello 2. It is developed by the Electric Coin Company, aka ZCash team. And it's now released in MIT and Apache 2.0, so feel free to use it. It can build plonkish circuits. What we mean by plonkish circuit is it contains the proving system of the PLONK paper and custom gates and lookups, and that's the core of our talk. I'll talk about that later. And PSE, we have a fork of Hello 2. We did some customization that works for the for the zkevm project. So the first half part of the talk, I'll be talking about some differences. First, you might be very curious about what's the main difference between Hello 2 and ZCash. So in ZCash, you can build circuits and that use the Growth 16 or PLONK. But in Hello 2, it's mainly PLONK, but with extra support of custom gate and lookup arguments. This is what makes plonkish system powerful. And in ZCash, you can use PLONK too, but like we said, it has no custom gate and lookup arguments as far as I know. But it gives you the universal setup benefit. More about it later. The arithmetization scheme is PLONK has itself has a very special arithmetization scheme. The arithmetization means that you have to turn your application logic into multiplications and additions, those kind of arithmetics. Unlike you, when you program in your usual language like Python or Rust, you build your application logic with if-else, with for loops, with those kind of things. But to build a circuit, you need to turn your application logic into numbers adding together, multiplies together. So that's what arithmetization means. And ZCash use RNCS, and so this makes when building Hello to Circuit and ZCash, we need to have very different mindset. And can we verify a proof in Solidity? In ZCash, that's like you can done it from since beginning, but Hello to there are some prototypes, and I hope soon we can do it. And if you are interested in this part, talk to me. And how do you build circuits? In ZCash, it's a domain-specific language. It has a language that looks like JavaScript, and you build a circuit using that language. But in Hello 2, it's all Rust API. So you need to compose your circuit with that API. So that's the big developer experience difference. And yeah. Question? Oh, sorry. Okay. The difference between PLONK and Growth 16, it has a different arithmetization scheme. And the trusted setup, the PLONK is universal. That means you can reuse the phase 1 trusted setup and apply it on different applications. But Growth 16 is application specific. When you build a new application, you need to do a phase 2 trusted setup. If you want to change some circuit code in your application, you need to do another phase 2 trusted setup. PLONK is a little bit more convenient. Proof size, Growth 16 has minimal proof size. PLONK is larger, and depending on what gates you use. What PLONK can give you is it can improve the arithmetic operations with custom gates. It can improve the bitwise operations and range check with lookup arguments. And for Growth 16, if you want to do like bitwise operations, it takes a lot of constraint to build that. So that's why like usual hash functions like KCALC or SHA-256, it's very expensive to build in Growth 16. And the difference between the PSE fork and the ZCash upstream is that, for example, the supported curves are different. ZCash upstream use pasta curves, and PSE fork, we want to support BN256 curve. We want this curve because we can verify this curve using Ethereum's precompiled contract. The Ethereum has a pairing precompiled contract, and it currently support BN curve. The proving scheme, ZCash is in a product argument, and the PSE fork use KZG commitments and also strong optimization. And zero knowledge, For ZCash, privacy is the uncompromisable default. So circuit always comes with zero knowledge. And for PSE fork, sometimes we want to explore scalability more, so we want to make it optional. And there are also extra features like GPU or memory optimizations by scroll and braid from looping, and we have pro-silent transcripts. We have EVM verifier supports, and in our circuit report, there's a constraint builder. They can build very complicated circuit, but with more abstractions. So, any questions so far? Okay. Okay. Oh, sorry. Okay. So, thank you. So now let's talk about some Hello 2 basics. So in Hello 2, you have to think in the a grid of columns and rows and cells, like Excel spreadsheet. The column is polynomial, and a row is like the roots of unity is like x coordinate, and the cell is the evaluation of the polynomial on that roots of unity. But I think this information is more useful if you want to know how it works behind the scene. But generally speaking, more column is more costly because you need to have more KZG opening for curves, and if you utilize more rows, more cells, it's more cheap because they are all in same polynomial, and it's basically free. And here at the right hand side, you can see this is circuit you can print out with Hello 2. This circuit has 4 columns. The red columns are advice columns. It is you fill in the cell. Prover fills in the cells when in the proving time. And at the right hand side, there's this bluish, purplish column. It's fixed column, and you assign the value at the compiling time. And the green cells are the cells that has values filled. And there are also instance columns. I'm not showing here. It's public input, and prover fill in those public values at the proving time. And the reddish, pinkish advice columns, they are kind of like private values. And okay, and in Hello 2, you have 3 building blocks to build your circuit. One is custom gates, one is lookup gates, and one is the copy constraints. We'll go into them one by one. So a custom gate is the expression that cells in the gates must hold. For example, you can have a custom gate that reference to a column A, to a column B, or column C. You can reference to the current cells at the current row. You can reference to the cell at the previous row or next row. they come in with the extra cost, but that's what you can do. You can even reference to the like 20 rows later, and you this gate will apply to the every rows of the circuit, and unless but you always need to define a selector. The selector is 0 or 1, and so when it's 1, it means we need to enable the check for that expression to hold. But if it's 0, then we don't want to check the expression at that particular row. So for example, this is the expression we defined. We want the selector at a particular row times the expression on the right hand side to be 0. So if the selector is 0, then no matter what the right hand side is, it's always 0. But if the selector is 1, and then the right hand side must be 0. So the A minus B must equal to the B next. So this is how you define the custom gate. You choose cells and define the selectors and define the equations and make it 0. For example, this is the Fibonacci example I borrowed from Inton's repo. Fibonacci series is a series of start with 1 and 1, and then the next one is the addition of previous 2. For example, 2 is 1 plus 1, 3 is 1 plus 2, 5 is 2 plus 3. So what we can do, we can define 3 columns, left, right, and sum, and then fill in the previous 2 values and add the sum at the next column. We can define a custom gate that takes the current cell of the left column, have the current cell of the right column, and take the current cell of the sum. And we want to we define a selector called qfit. When it's 1, that means the gate is enabled in this row, and enabled in this row, but not in the last final row. And so we are able to check the circuit in this way. Note that we still need the copy constraint to copy the sum to the right and sum to the left. But the emphasis is the custom gate now. And this is not the only way to define custom gate for this particular circuit. You can also define a custom gate like this. We can use the left, right, and the next cell of the right. So the next cell of the right must equal to the left plus the current cell of the left plus right. So here we reduced 1 column, but we add another cost of opening the next cell. So this is custom gate. And the other powerful component for the Hello 2 is the lookup argument. And the lookup argument is useful to do range check and bitwise operations. So to define the lookup argument, you still need a selector and the current cell at the advice columns, and then you give a column of the table you want to look up. This is a range check. So for example, I want to check if the advised value is between 0 and 7. So we can define the range table. It's a fixed column. It has value 0 to 7, and then the look argument can check that if that selector is enabled in the first 3 rows, then the first 3 cells in the advised columns must be within that range. There must be a corresponding value in the lookup column equals to that advised cell. For example, 6 exists in the range table here, 2 exists in the range table here, and 4 exists in the range table here. And if you witness something like 9, then the lookup will fail. So this is used for building range check. If you think about how to do it in ZCash, it would be a huge pain. And the other useful thing is to build a bitwise operations. You can define 2 lookup columns, and that has like A, X, or B, the value of A, X, or B, and they must equal to the XOR result. So yeah, let's look at argument. And the final component is the copy constraints. The copy constraints bind to cells so that their values must be equal to each other. For example, if this cell's value is 100, the other must be 102. It's the cheapest constraint and use as much as possible as we can. And yeah, so that's the 3 basic building part for the Halo 2 circuit. So I give some one like a real like example code. So so usually like you want to break down your application logic. It might be very complicated. For example, a decentralized mixer, you have like hash, you have identity commitment, different components. Then you start by defining like configs for the individual components. It contains the selectors and columns it interact with. Then we define the constructor, and that defines a custom gates or lookup gates inside. You can see this expression. It creates a gate, and then it queries selectors and query advised column at the current cell. And there are some other expressions that might from constant, from fixed table or instance table. And then once you're done, yeah, the first part is define the gate. And then the second part is define an API of how to assign values to the cells. So in this assign API, you enable the selector, and then you assign the value into the advised column. You specify a name, specify a column, specify which rows it at. It's called offset. It's offset relative to some regions, so you don't need to remember the absolute row of the circuit. You just specify the relative position of the row. and the dummy is the value to fill in. Now that the prover and the verifier then runs the same assignment API, but the difference being the prover run this to assign the cell and also the values in the cell. But for the verifier only assigns the cell. But if it's a fixed column, it assigns the value too. But for the advice columns, the verifier has no way to know the value at a compiling time, and it makes no sense for the verifier to know the actual value. So this value has like two outcomes. One is a known value, one is unknown value. So the verifier when the verifier runs the assign advice, the verifier does not assign the value to the cell. And then you start compose some like parent config and like organize your subconfigs in that parent config. Then finally you define the circuit trait. So this circuit trait you need to define your config here. The EQ1 config we defined in previous slides. And then you create columns here, and then there's a synthesize, you run the assign API. Finally, you can use the mock prover to verify the code. So this my circuit is it is for prover to run. It gives a known value. Oh, sorry. And then you select the polynomial degree. This determines like how many rows you can use. Usually you might choose like k equal to 16. So that means you have 2 to the 16 rows you can use. But like in our example circuit, this is a very tiny circuit, so 3 is enough. And then you run the mock prover and run the verify. Then this is usually used in testing, but like in a real production, there is another real prover struct, but you still like filled in the same like similar arguments into that into that struct. Yeah. So yeah, this is give you that glimpse of how the dev experience of the Hello 2 might looks like. And there are some advice here, but I don't want to go through all of them until you really try really stuck in there. I just write them here as a footnote. So yeah, that's the end of my presentation. Any questions?
Yeah, I've got one. So the PSE team swapped BN, or I guess the pasta curves for BN254. Is there, or do you want to talk a little more about why that decision was made?
Yes. So because like eventually you want to like we want like most of our application, we want to verify the proof in on Ethereum, and that the choice of the curve matters, because like the we have a precompiled contract on Ethereum that only verified BN 256 or 254 curve, and there are plans to support like BLS 12381 in the future, but BN 256 is what currently works. So that's why we choose the BN curve. That's a curve that you can verify in on Ethereum today. Like almost all our projects and applications use BN curve. So that's it. Makes sense. Or do you want me
Yeah.
to?
So I guess then my real question is the flip side of that. The pasta curves. What is there to be gained by using them if the decision was made to kind of just switch back to BN254 for like compatibility?
So pasta curve is specifically built for the ZCash applications. Okay, I don't know much about pasta curve, but like it's essential for the recursion proof that required by the Zcash client, or the proving scheme.
Yeah, the cyclic curve. So if I wanted theoretically to build something recursive, I would need to use pasta, or could I still do BN254?
I think you have to do pasta.
Okay, that's good to know. Thank you.
Okay. Which table? Where? Uh, yeah, sure.
So I guess if no one else has got anything, the other thing that's really kind of crazy is optional ZK. Personally, I'm a little more motivated by the scalability. Anyways, how is that just kind of you take all of the parts that go into the algorithm and then you strip away the zero knowledgeness part, and it all still proves like that it exists and you can use it?
So okay. The the ZK for the PLONK system is actually adding blinding factors at the end of the rows, roughly speaking. So to make it optional, that means we want to remove those blinding factors and like adding more rows at the bottom of the circuit. Not sure if that answers your question.
Yeah, totally. Um, does it
Yeah.
is it as efficient? Like in that, it looks like it's 20 or 30%, but that's like visual. It how efficient? How much more efficient is it to omit the blinding factor if that's something you know off the top of your head?
Uh, I I actually have no data of this, so
Yeah,
yeah.
it's little. Okay, very cool. Anyways, thank you. That definitely did clear it out.
Um, oh, good question. I actually don't know the detail. But like the bottleneck. I think that the bottleneck of the proof specifically on zkVM is that we use a lot of memories like 100 or 200 gigabytes, and so it would be like more efficient, or to reduce our like cost of computation by like optimizing the memory, or like if you can use GPU to speed up the proof. That means like in the in ZK rollup you can create a proof faster. And yeah, so you can if you can create a proof faster, that means you can finalize a transaction faster. That makes sense. Okay. How do you do the push to talk? Tyler?
Yeah, I'm looking up the key now.
It's in user settings, and I had to set up my own bind.
Oh, it's not on by default. There's not a default button.
Yeah.
Okay. I will turn voice activity back on. Anyone should be able to ask a question now.
Yeah, sure. Wow. oh, sorry. I think we started zkevm since 1 year ago, and yeah, and like I think I've been in PSE for like 2 more years. At first, like I helped on some semaphore projects and Messi projects, and then the harbor optimistic roll up, and then the zkevm.
Oh yeah. Yeah, I've spent the past month going down the rabbit hole. Aside from all of it, it's definitely a big leap from CIRCOM. You really have to understand the fundamentals of the math going on, whereas you can kind of fake it with CIRCOM. So it's
Hello，为啥？
I just wanted to give them a chance to ask if they. Yeah, I don't want to like dominate the. I have a ton of questions, but yeah, if anyone has questions, please interrupt me. But I guess I'll fire off one more question that's pretty related to what I'm doing. So we built privacy preserving proofs in CIRCOM for a battleship game, and eventually we want it to be recursive, so we had to switch from CIRCOM to Halo to even accomplish that. But now we're back to square one with the proofs. And right now we have a 10 by 10 board, which is basically they're binary 0 or 1. And what I'm trying to figure out right now is whether I should have a region. I think that's the right way to refer to it, like a region that is 10 by 10 cells, or I should have just like a single cell that I then like extract out as a bitmap within the code and then work with it that way. I'm wondering if you have thoughts on that.
How do you verify your proof?
Like what constraints do I place on it?
No, I mean, okay, yeah. Let's talk about what kind of like validity condition you need to check. Like what makes like selecting a cell valid?
So there's a range check that makes sure it's between inclusive 0 and 9. And then there's also some more custom logic that makes sure there's an X and Y and then a Z, because it's like battleships. You start from one spot and extend based on the ship's length. So then we have to check basically if in this 10 by 10 grid, any of those placements overlap. And we want to prove that basically once we've placed them all of the cells are still, now that I'm actually talking about it, we do probably want it to be cells. Yeah. So you would want to check though that once you've placed them all down, they are all still binary. None of them are like 2 or 3 possibly. But yeah. if that makes sense.
Yeah, that makes perfect sense. So, yeah, and how do you need to make a commitment to like, for example, hashing all the grids together to get a public input?
Yeah, so that's the very first step of playing this game is to commit to a certain board state. So essentially exactly that, whether we run it through like Poseidon or we're looking at like Sinsamilla because that seems to be popular with Halo 2. But yeah.
Oh, okay. So you just like encode the board as a like binary string, and then or maybe like in a as a field element, and then run Poseidon or something to commit that.
Okay.
Oh, and that was a question.
Yeah, I mean, I think actually almost talking through it, because a lot of what you showed with like the visuals, for some reason it just clicked a little more with how the cells work. But I think that it might not be possible, it would be the best idea to have 10 by 10 cells
Yeah.
to do this check rather than having it be a single cell.
Oh, I see.
And I guess yeah, if you think that's the wrong idea, please let me know. But otherwise, I think I'm going to go forward with that.
Yeah, I think it generally makes sense. And yeah, yeah, just thinking, like, okay, but like, when you want to do a placement of a ship, then you only need to like select the cells that, for example, your ship has takes 4 cells on the checkboard, and you only need to check that 4 cells that's not like having a value 2 or more, right?
So I could potentially not check every single cell, is what you're saying?
Yes, that was.
Ooh, okay. Because I did that with the previous one. I did have to check every single cell. Okay, that's very cool. That would be material like upgrade to show to it.
Oh, glad that's helpful.
Yeah, thank you so much.
Thank you for sharing me your project.
Yeah, I hope to share more soon.
Hi, hello. Can you hear me? Yeah. Oh, okay. Hi, CC, great talk. I have one question. What's the trace format should I take when I write a circuit using Hello 2? And what are the main considerations? Thank you.
Sorry, I didn't get the question one. Can you repeat
My
again?
question is what's the trace format should I take when I write a circuit using Hello 2? Trace format.
Trace format.
Yes.
Do do what's a trace format? Yeah, sorry.
What's the trace?
Uh,
Uh, I want to let my friend.
Yeah, if you feel more comfortable in Mandarin, I can translate it for you.
Can I speak Chinese?
Yeah. Feel free.
OK。就是使用 Hello To 编写电路的时候，应该采用什么样的trace 的格式
Place 的格式，
？Yes。
我有点听不懂。
听不懂。
对，你说 trace 的格式是像什么？
Wait me a minute。
Yeah, sure. Sure. Yeah, sorry. I still have trouble figuring out for the Chinese part. Like, I think he mentioned some.
Hello。
Yeah.
嗨
你说。
谢谢。好，我刚刚问了一下我朋友，就是什么是 trace format，他说是一个 table，它有多少行多少列，然后每一行每一列它里边的一个 cell 的内容大概是什么样的。
Oh. Okay. Good question. Okay. So I think the question is like we say that the Hello To works on columns and rows, and like how many columns we have, and then like how many rows we have, and what's inside a cell. So I think the answer is like you can have as many columns you want, but like every new columns you add adds more proving cost and verifying cost. Also like proving time, verifying time, and then the cells, the rows like. So we talk about like you choose the value of k. This one. You have the like maximum rows you can use. So for example, if you choose k equals to 16, that means you have a polynomial degree 2 to the 16. But there's a maximum depending on what curve you use. For example, in BN256, there's a property called like two adicity or something like that. Like I think it cap your maximum possible rows at like 2 to the 26 or 28, something like that. So like you cannot use like as many rows you can use, and also like adding rows, also adding the overhead of FFT operations, and it means that like you have more proving time. And yeah, so that's column and rows. To summarize, like you can add more columns and more rows. You can add unlimited columns, but not unlimited rows. But then they all comes with proving costs. But the cell, what's inside the cell is a field element. It's basically a very big integer, but like taking modules to the curve order, like it's treated as a big integer, and it's a positive integer. Yeah, not sure if that answers your question, Pen.
Yes, absolutely. Thank you.
Thank you, Payne. Thank you, Payne.
And I have another question, and I ask this for my friend.
Yeah, sure.
Can I speak Chinese
Yeah,
to
please.
describe this question? Thank you. 就是如果我要写一个 custom gate 的话，比如说有3个输入1个输出，那么应该是3个 advice column 还是1个 instance column？是这样吗？就3个 advice column 1个 instance column， 就3个输入1个输出。
OK，好，我先帮你把那个问题翻成英文。
好，谢谢。
对。So the question is that if I want to program a custom gate and it has 3 input, 1 output, and what kind of column should I use? Like is it 3 advice column and 1 instance column? So my answer to this question is that the custom gate does not work like that. It's not a gate like a physical circuits per se. Or maybe gate is rather confusing. It only defines a set defines an equation that must hold. So it's there's no such thing as like 3 inputs or 1 output. You can reference to as many cells or like different cells as you like. You can compose arbitrary expressions you like. You can, for example, you can like reference to cell A or cell B, multiply them together, add to another cell D or something like that. So I guess like you if you want to simulate a gate of like physical circuit, like for example, you have 3 inputs, 1 output. You can define 3 cells as input, 1 cell as output, and you can choose that cells from either advice columns, from fixed columns, or instance columns. You can choose it arbitrarily, like choose anything that fits your need. But let me repeat here. Like the advice column is for private input from prover. Instance column is the public input from prover, and the fixed column is the value is assigned at the compiling time that both the prover and verifier has this value. So I guess depends on what's your application logic. Choose what columns you need. Does that make sense?
I see. Thank you, CC.
Thank you, Payne. Thank you, Charlie, for hosting. Thank you everyone for coming. Thank you, bye.
Thank you.